Good afternoon, everyone. I am Allison McKay, Chair of the Civil, Environmental, and Geodetic Engineering Department. It's my pleasure to welcome you to the CEGE CONNEXT quarterly lunchtime seminar series. We started this program to highlight the creative and amazing research that's happening in the Civil, Environmental, and Geodetic Engineering Department right now. And the full value of that work really occurs when that research is able to inform practice and policy. So this series is an opportunity for you to hear from faculty as they share their perspective on recent innovations and things they're doing that are relevant to practitioners. So we're happy to connect with you today, and this is really just a highlight that the department continues to be a resource for you after graduation. Today, it's my pleasure to introduce Dr. Ethan Kubatko. He is an associate professor in our department. He's an environmental engineer who studies complex hydrodynamic systems, and his particular innovation is building efficient and dynamically adaptable models that allow his group to obtain insights into multi-hazard impacts, so things such as coupled hurricane surge with coastal flooding. So he's going to share some of the latest things from the CHIL, the Computational Hydrodynamics and Informatics lab that he directs with graduate students and undergraduates in our department. So I request that you please drop questions in the chat function at any time during the presentation, and I will moderate those in the Q&A session after his presentation. So pleasure to welcome you, Dr. Kubatko.
Thank you very much, Allison, and thank you all for being here. I'm very pleased to see one of my former students on here. Hi, David. All right. Can everyone see that?
Yes.
That's great.
Okay. All right. And the volume is okay? Okay. Um, so yeah, as Allison mentioned, if you have any questions as I'm going over things, I'm happy to address them. I'd like to keep this on the informal side, so if you want to interject while I'm going through, that would be fine with me as well. And as Allison mentioned, the name of our lab is the CHIL, which stands for the Computational Hydrodynamics and Informatics Laboratory. And my running joke when people ask me what informatics is, I say it's the I in CHIL. All right, so today I'm going to just kind of give a brief overview of the types of things that we do in my lab. And hopefully you find it mildly entertaining, and hopefully you learn a little something. And if you do both, that's the ideal situation. Let me go ahead and get started. So I want to start with, so at the beginning here, I want to highlight, so a large part of what we do is simulation of hurricane storm surge. So at the very beginning here, I just want to highlight two hurricanes that have been very noteworthy that have made landfall in the US. And the first is Hurricane Katrina. And I'll explain why I'm highlighting these two particular storms as we go. I want to start with this video. This one is not a computer simulation, but rather just a video made up of satellite images showing the formation and then the landfall of Hurricane Katrina. And I like to show this because I think it really makes the point of how large and powerful these storms are and can be. And so let me just pause it here. The storm formed in the Caribbean as a tropical depression, and then it crossed over the state of Florida. And then as it moved into the Gulf waters, they were unseasonably warm for that time of year. And so the storm intensified rather rapidly, which you can see the eye of the storm right there, and before it eventually made landfall in New Orleans. And New Orleans has the unfortunate situation of a lot of it is actually below sea level. And it's sitting, so here's downtown New Orleans. Let me put in the laser pointer here. Here's downtown New Orleans in this area. And it's basically sitting you can imagine sitting in kind of a bowl between Lake Pontchartrain to the north and the Mississippi River to the south. And so these areas are very susceptible to flooding. Now they have at the time, had a lot of levees and flood walls built to serve as protection, but the magenta lines that I'm showing here are actually where failures occurred. And as a result of that, you can see that there was extensive flooding, which is shown by the blackened areas here, all throughout downtown New Orleans. So this next picture here shows one of those areas where, for example, uh, entire neighborhoods, residential areas got wiped out from the floodwaters. And here you can see the old flood wall that was on the previous structure, and the gravel here is actually new construction that was taking place. But you can see that all the homes were destroyed in this area, spare a couple here that were actually just protected by the fact that this barge washed up on shore and diverted the waters around them. The second storm that I'll highlight is Hurricane Harvey. This one made landfall in Houston, and it is notable for the amount of rainfall that actually occurred during the storm, with some areas reporting as much as up to 60 inches of rainfall accumulating over the course of the storm. And apparently, the National Weather Service actually had to add colors to their rainfall depth scale here after Harvey to account for situations where they had more than 30 inches, which is this kind of purple or pinkish color here. And as a result of that rainfall, there was significant inland flooding, especially along the highways, and this is just a picture showing that. So a couple facts that I'll note about these two storms. So first of all, and the reason why I'm highlighting them, they're the two costliest tropical cyclones that have occurred in the Atlantic Basin. Both of these storms are estimated to have resulted in around $125 billion of damages. Yes, that's billion. And Katrina is the deadliest U.S. hurricane since 1928. Around 1,400 people lost their lives. Hurricane Harvey has the distinction of being the wettest U.S. tropical cyclone on record. And like I mentioned, some areas recorded up to 60 inches of rainfall during the course of the storm. And on this last point, this actually highlights the need to consider what's referred to as compound flooding, which is some of our latest work, where you're looking at flooding effects due to both not only surge, but also rainfall. So I'll highlight some of those results towards the end here. So the question is, for situations like this, how can we help as engineers? And one way we can do this is by providing engineering tools that can aid in the planning and design of strategies that aim to mitigate the impact of these types of disasters. And how do we do this? Well, ultimately, we do this by hopefully providing reliable data that can help inform and make sound engineering decisions. So that's what we're ultimately shooting for with our engineering computational tools. If we drill down just a little bit and we start asking, okay, exactly what kind of data do we need? Well, we have to help answer questions like what measures can we take to help protect lives and infrastructure against these powerful but infrequent storms? And more specifically, we have to answer questions about the physics, right? So how high is the water rising? How fast it's moving, for example? And as a result of it moving, how much force is being exerted on the structures? So I want to outline the remaining part of this discussion in terms of the three kind of key questions. So the first one is just addressing what exactly are we trying to predict? The second one is once we know what we're trying to predict, how do we compute our predictions? And then finally, once we have the predictions, how accurate are they? So focusing in on this first point here, what are we trying to predict? Well, the models that we develop are general computational fluid dynamics models of the ocean, river basins, and estuaries. And they can be used for any number of different applications. So I've just listed some of them here. For example, we can use it to compute coastal ocean currents, hurricane storm surge, for example, tsunami waves, and then related processes that are a result of the moving water. And so, for example, shoreline erosion or contaminant transportation. I'm going to focus in particular on hurricane storm surge whenever I show the results from some of our models towards the end here. So just a little bit of background on storm surge. So it's an offshore rise of water that's associated with a low pressure weather system, which is typically found in a hurricane. And storm surges are caused primarily by the winds pushing on the ocean surface. So actually through the application of a shear stress on the surface of the ocean. And there are some secondary effects due to pressure as well as the bathymetry of the body of water that you're dealing with. So in this picture down below here is just showing, for example, first of all, we can see mean sea level. And under normal circumstances, we might have a high tide on the order of 2 feet. But as a result of surge, that can be an additional 15 feet in elevation, which of course results in the flooding. Now, as I mentioned, oftentimes we have this effect of what's called compound flooding, and that's flooding caused by 2 or more flood drivers. So a lot of times you're not only getting the winds, which are driving the surge, but you're also getting rainfall, which is resulting in runoff. So you're getting flooding occurring from 2 different causes, and these different causes can have nonlinear interactions, which can intensify the flooding results that you get. And one reason that we're interested in looking at this is that some recent work has shown that there has been increased risk of compound flooding in most major US cities from both storm surge and rainfall. And the bit of an issue is that the existing models generally account for surge, so the wind-driven surge, but they don't take rainfall into account. So those are some of the latest developments that we've done within our models to try to account for this effect. All right, so those are the kind of, if we just think about the first question here, what we're trying to predict. I'll pause here if anybody has any questions for me so far or anything. No? Okay. All right, so then the question becomes, all right, we know what we're trying to predict. How do we compute our predictions? And I like to think about this in terms of we kind of need 3 basic ingredients in order to compute them. So one is we need a set of fundamental laws that govern the physics of the problem. So for example, one that everybody is familiar with is Newton's second law. And expressed in simple form, it's just that force equals mass times acceleration. And this, of course, can be written as a differential equation in terms of velocity. So for the hurricane model, we're actually solving a set of 3 partial differential equations, which at first glance look a little confusing, but they're actually pretty simple at a high level. So it just consists of the conservation of mass, which is the first equation here. And then these next 2 equations, although they look pretty complicated, it's just an application of Newton's second law to the water. And what we're solving for, given that we have 3 equations, we can solve for the 3 unknowns. We're looking for the height of the ocean, or the water surface elevation, and then we're solving for the depth average velocity of the water within the ocean. Another thing that I want to point out is, although these look complicated, they're actually written in a somewhat simple form because there's a lot of additional physics, empirical type physics, that's buried in these last 2 terms of f of x, fy. So for example, we have to account for bottom friction, which we compute using a standard quadratic parameterization of the bottom stress. And in order to inform that, we use Manning's coefficients depending on what type of land we have. So whether it's over open water or whether or not we're in a forest, for example, or shrubland, those values and the bottom stress as a result of that will change. And then the other major factor that's summarized in those terms are the wind stresses. And of course, that's the primary driver of the flow when we're looking at storm surge. And this takes into account land roughness, and it makes adjustments depending on the upwind roughness and the level of local inundation in the presence of things like tree canopies, for example. So there's a lot of physics that's built into the models and a lot of parameters that are required, which requires us to have input a lot of data into the model and in order to try to get accurate predictions. So that's the first thing. In order to compute our predictions, we need this set of fundamental laws. So again, in the case of the hurricane storm surge model, it's these three equations that I showed. The second thing that we need is we're going to solve those equations over a particular area or problem domain. So we need a digital map or mesh of the area that we're looking at. So for example, in the case of Katrina, we're looking at New Orleans. And I'm showing here an example of a typical problem domain mesh that we would use. At first, this is a little maybe difficult to see, but if you look in the black space here, for example, you can see the state of Florida. So I'm showing here's the bathymetry of the Gulf of Mexico and the North Atlantic. And in order to simulate our hurricanes, we include this entire region, and we use finite element methods, if anyone's familiar with those, which requires the use of a mesh in order to represent the problem domain. And so to show an example of just one of those meshes here, and although you can't see, but you'll see it when I zoom in a little bit here, this is made up of a bunch of small triangles that can vary in size. And so, for example, they can get smaller, which ultimately would lead to more accuracy as you approach, for example, the continental shelf and then the shore. So this is showing, for example, the element sizes that we're using. So those are the colors here indicate the element sizes, where you can see that out in the open ocean, where the physics is relatively simple, we can use larger elements, which transition into smaller sized elements as we approach the shore and as we get into the particular area of interest. So for example, if we zoom into the New Orleans area here, you can start to see a little more detail. The area right here is Lake Pontchartrain, or I'm sorry, downtown New Orleans with Lake Pontchartrain to the north. And you can see the Mississippi River and the Mississippi River Delta here. And so now you see the blue areas here. As we zoom in, we're getting elements on the order of 50-ish meters in those regions. And again, the idea being that you supply more resolution where you want more accuracy. If we just will do one more zoom in here, I want to point out that a lot of these brown lines that you see here, those are levees and flood walls that are input into the model to represent the protection structures. All right, so we have our set of fundamental laws, we have the area over which we're solving them, and then finally, we need some sort of computational tool that could be used to help predict the movement of the water. That's where my students and I come in here. Here we are working busily at our computers. And so if we put all these things together, right, we take the fundamental law, we take the mesh or the map that we have for the given area, and then we have the initial and boundary conditions. So for example, this would include wind forcing. We put them all together. We apply our finite element method, right? So we turn the crank here. And ultimately what this does is it converts all of this information into a giant system of linear equations that we need to solve. And so you can imagine, for example, this vector here is just the set of unknowns that we would solving for. So for example, the water surface elevation. And let me display this. And that, as we get those results, that ultimately then gives us the computer simulation that we need for a given situation. All right, now I won't say much about the finite element method other than the fact that you have to use one of these meshes or a triangulation of your problem domain. And then you pose the problem in what's called a variational form. I won't get into the details of that, but the basic idea is that if any of you remember from taking fluid mechanics or something like that, right? We have this concept of control volumes. We can think of each one of the triangles that we have in the mesh as a control volume, and we're basically keeping track of what comes in and out of a given element in order to solve our problem. I like to say that that kind of quick summary is the finite element method in a nutshell. And nobody has their microphone, so I can't hear all the laughs that I'm getting right now. And I'll note that one time I had I gave this talk, or a similar talk to this, in front of a group of mathematicians. And one of the mathematicians raised his hand and corrected me and said, this is actually finite element method in nutshells, plural. So, of course, he was correct. All right, so we have this big system of equation. Oh, good. I got at least one chuckle here from David. Thank you. Um, for the hurricane simulation, we're solving three equations that I showed, right? And we're solving those at each node. A node just consists of each point of the triangles. And so for that mesh that I showed, for example, we have in the order of 2.5 million nodes or vertices. And again, we're solving three equations at each one of those nodes. So that means we're solving 7.5 million equations just to get the surface elevation and velocity at each point. Now we have to remember that these are dynamic models, right? So we're doing this at each model time step. And let's say a typical simulation, just for easy calculations here, let's say a typical simulation is 5 days and we're using a 1 second time step. That means that for 5 days of simulation, we have 86,400 seconds per day, and we're solving 7.5 million equations per second of simulations. That means we have to solve 3.24 trillion equations for just one of these simulations. So I don't know about you, but I consider that a lot of equations. And the way that we can do that is by taking advantage of supercomputing resources. So I want to just do a little digression here into this idea of what are called flops. So a flop is just a floating point operation per second. So a floating point operation is basically everything gets boiled down to you have addition, subtraction, multiplication, division in your codes. And the flop will, this flop count gives you how many of those operations you can compute per second. So for example, assume it takes person 1 minute to perform long division by hand to 10 digits. It's been a while since I've done long division, so it'd probably take me quite a bit longer. But if we roughly translated this to flops, that would be 0.017 flops. Computers, of course, can solve these equations at a much faster rate. So here I'm just going to show some of the flop counts that we have for doing these kinds of calculations. So for example, a simple calculator might operate on the order of 10 flops. And then I'm showing here at the bottom just some of the milestones that have been reached over the years. So for example, in 1961, they achieved what's called the megaflop, meaning that they could perform 1 million of these calculations per second. 1984, the gigaflop. And in 2008 was when what's called the petaflop milestone was reached. And then it's 10 to the 15th or 1 quadrillion of these operations per second. All right. And this is an article here that appeared that year where they achieved this at Los Alamos National Lab. And the picture here just indicates the supercomputing system, which basically is just, you can think about it in terms of a bunch of desktops that are put together, and they're all networked together to operate in parallel. After the petaflop, the next major milestone is the exaflop, and that was reached in 2020, and that is 10 to the 18th or 1 quintillion of these operations per second. And just a quick aside, I want to note that at the time, whenever the petaflop was reached in the summer of 2008, I was at the University of Texas at Austin, where they had a new supercomputer where they were attempting to be the first to achieve this result. They didn't quite make it. However, they were listed in the top 5 fastest supercomputers at the time. All right, so how are these supercomputers used for a problem? It's basically a divide and conquer approach. So if you imagine we have our problem domain that I showed previously, it's as simple enough as that we just break it up into smaller domains, and each one of those smaller domains then gets distributed to these CPUs. And they'll do their calculations just on that particular domain. And then, of course, it's required that they pass information back and forth between one another. What I like to point out is that these methods that we're using to solve the equations, so for example, the finite element method, these were, of course, invented or developed prior to the invention of the computer. And the question is, how did they do these kind of calculations beforehand? And here's your answer. Here's parallel computing in its most primitive form, where you basically have each person doing one calculation and passing it to their neighbor. And I found this paper on they call it the birth of the finite element method. And they note that in 1910, they actually used the word computer to describe the assistants that were employed to do the numerical calculations. And they paid a rather small wage here. So they paid a price of n over 18 pence per coordinate point, in which n was the number of digits that was used. And to add insult to injury, they didn't pay if the computers committed errors. So there's your first parallel computing paradigm right there. All right, so we've talked about the what we're trying to pick, or what the purpose of the computation is. Now we're moving into how accurate are the computations themselves that we're getting. So at first up, I just want to highlight a couple situations in the Western North Atlantic, where to begin, we're just going to try to predict the tidal flows in that area. Because if you can't get those right, then you don't really have any hope of doing more complicated problems like storm surge, for example. So this large region in the Western North Atlantic, and then two smaller regional studies, one on the East Coast, off the coast of New York, and then one in off of the state of Washington on the West Coast. So for example, if we look at this first larger domain here, and the orange dots in the picture are just where we have recorded water surface elevations that NOAA collects. And the plots that I'm showing here are showing the tides over a 14-day period. And there's two lines on each plot. And so the blue is the observed, and the red is the computer simulation. And you can see that we're doing a pretty decent job as we start to move down the coast here in terms of matching up the data. So this is, we can consider this the part of validating the model that we have in order to make sure that it actually matches reality. For these regional studies, so for example, here's one off of the West Coast in the state of Washington, where again, we have some stations where water surface elevation is recorded. And I like to show this one because it has a really large kind of tidal floodplain. So if you look at this is showing the water surface elevation in colors here. And all the brown areas are where you initially have dry land. Let me just play this and it'll cycle through one of the tides here. And so you can see one of the complicated kind of dynamics that we have to capture is this process of wetting and drying as the tide moves in and out, which can present challenges numerically. And here, for example, in those tidal regions, I'm just showing again how the model results match up with the observed data that we have. One thing to note is that, for example, out on these two stations on the left-hand side here, we do a pretty decent job. But within this smaller channel here, we do see some error in the model results. And that can be a result of something as simple as not providing enough resolution. So for example, providing smaller elements might kind of close the gap that we see here between observation and results. And then the case that I want to highlight on the East Coast is this area called Shinnecock Inlet. We were originally studying this problem. The Army Corps was looking at dredging operations in this region. So what happens here in situations like this is you get high velocities through the inlets, which can cause scour. And then as it enters out of the inlet, you get large shoals that get deposited in front of the inlet, and they have to constantly go in there and re-dredge. But one of the things that we looked at in this scenario was this idea of transport, contaminant transport, sediment transport. So for example, if we look at concentration of this sediment during the outgoing tide, you can observe some interesting dynamics. So there's some big jetties that come out here, and you get an eddy that kind of captures some of the contaminant there and then actually brings it back into the back bay area. All right, so once you've predicted the flow, then what you can do, and this is what we did in this example, is you can actually couple it to another model then where you might look at the transport of some particular quantity. All right, and then finally, I want to show results for those two storms that I highlighted at the beginning, starting with Hurricane Katrina. And the images that I'm showing here are, turn on the laser pointer here, maybe. Oh, sorry, bear with me here. Okay. So what we're seeing is, again, here is the area where we have downtown New Orleans, which you can initially see is it's all dry. There's no water on it. And the colors here indicate the water surface elevation, and the arrows indicate the wind velocity. So as I start to go through here, you'll see the eye of the storm come into play here. And a couple things to point out is, so for example, the hurricane is spinning around counterclockwise this way, and as a result of that, there's a levee on one side of the Mississippi River here, and you can see, for example, water piling up along that side of the levee. So the red colors here indicate higher water levels. And the other thing that I want to point out as we go through here is that as the storm starts to approach land, you can see now the wind vectors over Lake Pontchartrain are pointing directly down to the south, which is pushing all that water towards downtown New Orleans. And you can start to see some flooding occurring in those regions that were initially dry. All right, so of course you can produce all kinds of pretty pictures like this, but from that, then we need to actually compare to recorded data. So we do that in basically two ways. So one is we can look at recorded hydrographs. So the plots here are showing some hydrographs at various spots around the area. The red lines indicate the measured water surface elevation. Where you see these sharp vertical lines, that's where the instrument dropped off and didn't record. And then the simulated results are shown in the black lines here. So you can see we do a fairly good job of matching at a lot of these hydrographs. In particular, you can see that we match the peak surge pretty well as the time to peak. Now, another way that we evaluate our results is we compare to high water marks. So after the storm, USGS will typically go in and record high water marks, which might be something like a debris line on a house, like it's shown here. And we can take all those recorded high water marks and compare them to what we got at those locations with our model. And so here I'm just showing some results from high water marks, where the colors here indicate the level of error that you have. So just roughly speaking, greens and yellows we're doing pretty well, right? So that's in plus minus half a meter. And if we quantify that a little more, we found that about 75% of the high water marks were within half a meter, and the average error was about 0.39 meters. Next, for the Hurricane Harvey results, this image is just showing the progression of Hurricane Harvey. It started off on August 16, 2017, and eventually made its first landfall August 26th. The colors here just indicate the category of the storm as it approached land, so you can see it strengthening as it approached the Houston area. And then you can see, if you look at the path, how it kind of zigzagged here, and that's one reason why so much water was dumped in that region of this particular storm, because the storm kind of hovered around the area for a little while. And it first made landfall on this San Jose Island, Texas. And around there, again, there are a number of these NOS, or National Service recording stations. And in a recent paper that we had, we took our storm surge model and extended it to include these rainfall effects that I mentioned at the beginning. So we're now doing these compound flood simulations. And this, I think, is a nice result, which shows the importance of including rainfall. So on this plot, this is water surface elevation over a period of days when the storm made landfall. And there are three lines on this plot. The green line shows the gauge data that was recorded. And then the blue line shows that if we did simulated surge only with our model, and you can see that there's quite a gap between the surface elevations in that case. But if we also include the rainfall effects, then we get much better results. Still some area here that we need to investigate, but overall, in general, you can see that it really improves the results to include the rainfall. And then I'll end with these two pictures because I think this really brings the point home. So this is showing, again, if you look at high water marks in the area and compare the observed peak values, which are shown on the horizontal axis here, to the modeled peak values, we can get one of these scatter plots, right? And so the way that you can think about this is here's the one-to-one line shown in black here. And if the model were producing perfect results, right, all the points would be right on that one-to-one line. But if they're underneath it, that means the model's slightly under-predicting. And if they're over it, and that means it's over-predicting. And the colors here correspond to whether you get plus minus, for example, half a meter up to a meter. And on the right pane here, I'm just reporting some skill assessment metrics. So one would be the slope of the best fit line, which ideally we would want to be 1. So here it's about 0.75. This is the normalized mean absolute error, which is about 0.29 in this case. And then this gives us a bias negative, indicating that in general, the model is under predicting. Now, the results that I'm showing here are if we're doing surge only. And the important thing to note here is that this hit rate that I'm reporting, that's the number of high water marks that were actually shown to be flooded by the model. So in this case, only 23% of them were actually shown to be flooded by the model. However, if we include that addition of rainfall, you can see now we get a hit rate of 99%. So almost all of the high water marks were actually flooded with our model. We see an increase in the other skill assessment metrics. So for example, the slope of the best fit line is now 0.95, a lot closer to 1. The normalized mean absolute error dropped. And then the bias, although it's still slightly under predicting, improved as well. All right, so let's see. I'm approaching 40 minutes here, so I think that's probably good. So I'll just end with a quick summary. So first is that computational models, and I want to highlight here, when properly used, right? We don't want to just use them as black boxes, can be powerful tools to aid in making engineering and scientific decisions. And with increases in computational power and the corresponding increased use of computational model, there exist both opportunities and dangers associated with that. So the opportunity is that solution to many problems that were previously thought to be intractable are now possible. However, again, as I stress on this first bullet point, we don't want models just to become black boxes. And in order to prevent this, it's crucial that we have the education of students and professionals in computational methods and environmental fluid mechanics, which I view as part of my role. And with that, I would like to say thank you, and I'd be happy to take any questions if anybody has any. Hey, now I see 2 of my students up there. That's great. Mackenzie or Dave Dibling, do you have any questions?
Not questions, but I was just, it's interesting to see like how far things have come since just in I think 3 years since I was there. Very like it's really cool, really well done. I like seeing the progress of it. It's really cool to jump back in a little bit.
Yeah, thank you. Well, you're the one that started a lot of the rainfall stuff, right? So,
Yeah, seeing like the Hurricane Harvey stuff like took me back. I was like, I remember all of that.
yeah. Well, I'm glad you could join.
Ethan, there's a couple of questions in the chat. One
Okay.
asking how long the computations take, even with the state of like actual machine computation now. I loved the historic reference you made. That was awesome.
Yeah, so there's not a simple answer to that because it is a function of, how large your mesh is and what kind of computing resources you have. But I can give you just kind of a broad answer. So typically when we run at OSC, the Ohio Supercomputing Center, we might use around 800 compute nodes in order to do that. And it might take on the order of 2 to 3 hours or something to run one of the problems. So, um, not terrible, but we're always looking to improve that. Okay, should I just go to the next question here?
Sure.
Yeah. So David Straub, you ask, so is your hit rate only as good as the predicted rainfall amounts? Seeing that as the limiting factor. So I mean, it's definitely a factor, and actually we're looking at different ways and different data sources for the rainfall. So unfortunately, during tropical cyclones, so if we're doing hindcasting, for example, it's difficult to even obtain what the exact rainfall was because although they have things like rain gauges that collect the water, those aren't super accurate in the presence of a tropical cyclone. And there's a couple reasons for that. One is that when you get these very heavy winds, you have the wind or the rainfall kind of entering sideways into the gauge, so it's not actually capturing all the rainfall within the gauge. And then um, I think this is one of the funnier ones, is that some of the old rain gauges actually have this tipping bucket where after it obtains a certain volume of water, then it will tip out the water so that it can refill. But of course, as it's tipping out the water, right, it's not collecting the rainfall that's coming down. So getting accurate measurements of the rainfall is a challenge, and that definitely will affect our hit rate. Does that answer your question, David?
Any other questions? We're down here.
Yeah, thank you, David.
If there's not further questions, then I'll thank you, Ethan. Really appreciate that you could be here. And
Yeah, thank
as I know that you're also very skilled in the classroom to take super complex, yeah, lots of mathematics that can be intimidating for folks and really break it down into straightforward explanations and yeah, direct link to how your work can impact communities to help to think about planning to make them safer in these unpredictable situations. So really thank you for that. Um, I appreciate everybody who joined the call today, and I'll make a shout out for our next webinar, which will be on April the 8th. Dr. Min Liu, who's a geotechnical engineer in the department, will present about some of her work. Her specialization is thinking about infrastructure impacts that are happening in the high Arctic as a result of permafrost melting. And she does that work through kind of coupled thermal and mechanical stresses on soils. So look forward to seeing you all there. And we typically can follow up in about a week and a half with the credit for the CPD hours. If any of you had requested those will come to you through the email that you signed up for. So thank you, everybody.
you. All right, thank you all for coming.